So we say a function is continuous if at every point in the interval from like, let's say a to b, each one of these exists and they're equal to each other. So this right here with the little plus sign, that means the right-sided limit. Do you know what I mean by that? Cool. And this negative sign is the left-sided limit. It's saying the right-sided and the left-sided limit exist and are equal to each other. In other words, you say the two-sided limit exists. And it has to be equal to the function evaluated at that point. And if that's true for every point inside of an interval, we say that the function is continuous on some interval. When we talk about this informally, a continuous function is one where you can set down your pen and you can draw the whole curve without picking up your pen, right? Anytime you have to lift your pencil up off the paper, that would be a discontinuity, but this is continuous. The intermediate value theorem, you probably saw this in Calculus 1, but it says something like, if f is a function that's continuous on an interval, then for every value y that is between f of a and f of b, there exists a point inside that interval such that your function takes on the value y. So I'll draw a picture. So here is my picture, and this is going to be a, and this is going to be b, and there's some value of my function at a, and some value of my function at b. And what it says is you get to choose any point you want in between f of a and f of b, let's call it y, and as long as this function is continuous, then there exists some point in between a and b such that this function takes on this value. And the reason for this, I hope you're convinced, is that like, if I try to set down my pen here and draw the curve over to the other point, well, there's nothing I can really do that could ever avoid passing through that value, as long as I don't have some kind of discontinuity. So the point where we pass through that y value is the point that we're talking about. That's what the intermediate value theorem is saying. Again, probably saw that in Calculus 1, but it's important for today when we talk about the bisection method. Bolzano's theorem is a special case of the intermediate value theorem. Bolzano's theorem says if f is a function continuous on a and b, and suppose that f of a and f of b have opposite plus or minus sign, then there has to exist a point in that interval where the function is equal to 0. So now, here is a, and here is b, and let's say this is f of b, and this is f of a. So that f of a and f of b have opposite plus or minus signs. F of b is negative here. Then Bolzano's theorem is saying the same thing as the intermediate value theorem. There's got to be some point where this continuous function has to pass through the x-axis. You can't avoid it unless you have a discontinuity. So as long as we know my function is continuous, if I switch signs positive to negative, there has to be a 0 in between. And so the bisection method is a way to look for a 0 on a bracketed interval where we're relying on the Bolzano's theorem, right? We're saying I've got this bracketed interval, my function has opposite plus or minus signs on either end of the interval. So we know a 0 has to exist somewhere in that interval, and we can continue just by bisecting the interval until we get it narrowed down to what we want. So like in this example, suppose I don't know what this function is, So I can't see with my eyes exactly where this is happening. What I would do next, knowing that f of a is positive and f of b is negative, is I would cut this interval in half right here. And then I would say, now I'm going to scoot up my lower bound because I know that this point along my function is also positive. And so the 0 has to exist somewhere between the positive and the negative value. And then I would bisect my interval again here, test out what value the function has. I find out that my function value is negative. And so then I'm going to scooch in my upper bound, and my bracketed interval shrinks again. And then I bisect the interval again, like right here. And I test out what is the value of my function here. The value of my function is positive. And so I'm going to scooch in the lower bound of my interval, and then I bisect it again. And I find out that the function is negative here. So I'm going to scoot in the upper bound of my interval. And the idea is you just shrink your interval so that the function value at the upper and lower bound always has opposite plus or minus sign. Okay? So here's a quick exercise for you, especially if you brought your calculator today. Bring out your calculator and see what we get. It says, use the bisection method and a TI-30X2S calculator to calculate the value of square root 2 to within plus or minus 0.1. And when I say that, what I mean is, let's try to find x where x is the square root of 2. And don't type in square root of 2 in your calculator. Instead, I want you to do this. If x is square root of 2, x squared must be 2. And that means x squared minus 2 must be 0. So take a look at this function, f of x equals x squared minus 2. And then find the 0 of this function and the thing is, you need to have some kind of starting bracket. You need to start with some interval where you know that the 0 we're looking for is not lower than the lower bound and it's not greater than the upper bound. And so one thing we know is that the square root of 2 has to be greater than 1. Just because 1 squared is 1, and that's less than 2, so the square root of 2 has to be greater than 1. The square root of 2 also has to be less than 2, because 2 squared is 4, and 4 is obviously greater than 2. And so maybe our starting lower bound can be 1, and our starting upper bound can be 2. And it could help to make a little table here of like, what's my lower bound, what's my upper bound, what's my midpoint, and then what's the function value at my midpoint. And we could also keep track of what iteration number it is. So on my first iteration, A is 1, B is 2, my midpoint would be 1.5. What is the value of this function evaluated at 1.5? In other words, what is 1.5 squared minus 2? 0.25. Yeah, 0.25. And so if it's positive 0.25, what do I do for iteration number 2? Let me ask you, what is my new lower bound going to be? Sorry, another part I skipped here another little part I skipped, is like, what was f of 1? What's 1 squared minus 2? And what is f of 2? What's 2 squared minus 2? 2. So this function has a negative value at the lower bound, and it has a positive value at the upper bound. That's the picture. Okay, so now, back to my table. If at 1.5 the value is positive, what's my new lower bound? 1. What's my new upper bound? 1.5. Now what's my midpoint? 1.25. And what is the value of my function evaluated at 1.25? You said it was negative? Negative 0.44? Yeah. Okay, so if the value of this function is negative, and I'm going on for my third iteration now, what's my new lower bound? 1.25. Yeah. On each iteration of the bisection method, the midpoint either becomes your new lower bound or your new upper bound. In this case, since my function is increasing from left to right, then a positive value of my function at the midpoint is going to make the midpoint my new upper bound. And a negative value of my function at the midpoint is going to make that midpoint my new lower bound. It actually changes. If your function is decreasing from left to right, it's going down, then it's going to have an opposite effect. The plus or minus on the function at the midpoint will have an opposite effect on how you move the upper or lower bound to the midpoint. And since the lower bound changed, the upper bound stays the same this time. My new midpoint is going to be like 1.375, I think. What's the function evaluated at 1.375? That function. Negative 0.11. And since it's negative, that means my lower bound becomes the old midpoint. The upper bound stays the same. The midpoint between here is 1 point, what did you say? The midpoint between 1.375 and 1.5? This midpoint is just a plus b divided by 2. 1.4? 44? And that's good enough, right? Because this question is saying use the bisection method to calculate within plus or minus 0.1. Square root of 2 is like 1.4-ish, and so that's good enough for me. In fact, I guess 3 iterations was enough to do it. It only took us 3 iterations of the bisection method to get zeroed on this. Because square root of 2 is like 1.41, I think, and that is within plus or minus 0.1. Okay, but you see how the bisection method works? Cool.
But how would you know to stop at 1.3 whatever?
I know how to stop this time just because I know what the square root of 2 is. If I didn't know what the answer was supposed to be, like I didn't know what the 0 was ahead of time, then what you could do is you could look at the interval and calculate what's the width of this interval and then divide it by 2. Because whenever you select your midpoint at the end and say that's my answer, the distance between the midpoint in the upper bound and the midpoint in the lower bound is the same distance, and that's your maximum error that you could possibly have. Because we know for a fact that it's between A and B. The fact that we make it halfway through when we choose our answer means the maximum possible error, and our answer is half of the interval that we're left with. So I guess that's a good point. If I actually did not know what my answer was supposed to be, then that wouldn't be good enough, right? Because the maximum possible error here would be 0.5, then it would be 0.25, and the maximum possible error here would be 0.125. And that's still larger than 0.1. But here, the maximum possible error is 0.0625. If I say that this is my answer, I know it's at least within 0.0625 of the real answer for square root of 2. Good question. Other questions? No? All right, so we're going to do this in Python now. So I'm going to boot up my Python and see what we get. I think we already did this on the first day of class. Okay, I was about to say, I didn't do this in my free time, but it was already on the classroom computer, so I think we have already done this. So this is all it takes. First line, import numpy as np. That's just a library of commands. I'm setting my lower bound to, let's say, 1, and my upper bound to 2, because I know the square root of 2 has to be somewhere between 1 and 2. And then this is what we have. We've got a for loop. We've got a way to find the midpoint. This time I said C is the midpoint. But you can call it whatever you want. It's just a plus b divided by 2. And this time my function value is going to be the midpoint squared minus 2. And then we say, if my function is greater than 0, meaning it's positive, then that means I need to make my new upper bound equal to where my midpoint was. And if my function value is negative, I need to make my new lower bound where the midpoint was. And if my function is exactly 0, then that's awesome. I found the 0 and we can stop. So let's see how it goes. Boop. And if you want to, you can tell you can tell the program to just print what the answer is like that. Or you can just look up in the user interface here and figure out what the variable was. But there's a few things I want to point out. For one thing, I could get another iteration of accuracy, not completely for free, but just not in a completely terrible way either. If I do something like this. The one slight improvement I made to this code is I start by calculating the midpoint before I begin, and then I calculate a new midpoint at the end of every loop. Because that way I at least calculate the midpoint one more time. You know, that's going to allow me to cut down the maximum possible error by another half before I'm done with the code. And yes, it does mean I have to add 2 more flops in addition and a division, but it does prevent me from having to evaluate the function again, if that makes sense. So I'm doing the most I can. I'm being as efficient as possible this way. And then, well, and I guess maybe if I find, yeah, that's right. Okay, no, it's good. And then, what other thing was I going to point out? Oh, does this function, the way I wrote it, does this code work for both increasing and decreasing functions? Or does it only work for increasing your functions or only work for decreasing functions? Does that question make sense, what I just said? What this says is I calculate the value of my function. If my function is positive, then I'm going to move my lower bound, or sorry, move my upper bound. B is the upper bound. Move my upper bound down to where the midpoint is. Does that work for all functions, or only for decreasing functions, or only for increasing functions? Yeah, that would only be a valid command for increasing functions. If I wanted this to work for decreasing functions, then right here, I would need to flip the greater than sign and the less than sign so it would be ready to take a decreasing function. There's probably some way you could get around this. And what I mean by get around this is there's probably some way that you could make this work no matter whether the function was increasing or decreasing. And that's probably what you would want to do if you're going to do this in real life. Sometimes we know whether a function is increasing or decreasing, and sometimes we don't. So what could we do instead?
Figure out whether the function's increasing or decreasing by picking 2 points and going which one's greater.
Mm-hmm. Here's what I'm thinking. I don't know if this is the best way to do it, but I'm going to make a variable called f of a. Ready? And it's going to take this function and evaluate it at the point A. And then what I'm going to do is every time we every time we're comparing f, oh, hold on 1 minute. There's got to be a way to do this. I'm going to call this sine. Does that work? Yeah. There we go. Does that do it? Almost. I gotta switch these now. Less than, greater than. Haha, okay. I'm so pleased. So what have I done? What I did is I calculated what's the value of the function whenever I'm figuring out my lower bound to begin with, like the original lower bound I specify. And it should be negative, right? For this increasing function, it should be negative. And so now if the value of f times a negative is less than 0, that means f is positive, and that means I bring down the midpoint, or I bring down the upper bound to the midpoint. And now if f is negative, and I multiply by a negative, it becomes positive, and then I move up the lower bound to the midpoint. So with that little tweak, now this code will work whether the function is increasing or decreasing. By the way, some of you are familiar with Python, probably even more than me. And for others, you might need to see something like this. There's a way to define a function in Python, and I can't remember what it is. Is it function? No, that's not right.
Function.
It's just the word function.
Yeah. You can type in the name.
Are you sure?
Where's def? It's def.
Yeah, that's what was my first thought was. And it turned purple, so I thought that was it. Okay, so there we go. Now I can say something like this. There we go. And I don't have to keep typing out the function every time. I just have to change what that is. Boop. Okay, so the problem is now I can't use f as a variable. We can call it y then, if I can't use it as a variable. The function's name is f, and now the output is y. Let's try that. Boop. Same thing. Oh, well. int object. Let me clear the variables. Is it clear? CLC? No. What is... There you go. It's that trash can to remove variables. Okay, now it works. I think. Except why does it say it's 1.5? So maybe I have my signs wrong. Okay, because f of a should be negative, and if I have a negative times a positive, then it should fall into this category. And if the function is positive, then x is too big and you need to move in the midpoint. That's it, right? Somebody help me. What do I got wrong here?
Sign isn't getting used like.
Does the A and B need to be flipped there?
I don't know. It's just too weird. Let me just try to change the A and B and see if it works, and then if it does work, then we'll think about why. Nope, that doesn't work either, because now it's saying that my midpoint is like 1. So I think it was correct. Maybe it's this f is a problem. No, I think that's right. Oh, here it is. Okay, look. It was just saying y equals f of a, right? Now it's actually going to calculate the function value at the midpoint. There we go. Now it's perfect. Very good. So, you got to be super careful. Troubleshooting kind of sucks. And that's good. That's a working code. And it's going to work whether this function is, increasing or decreasing. A decreasing function we could try right now is 2 minus x squared, just to prove that it works. And sure enough, let's see if it still finds the right answer for midpoint. Yeah, okay. Now, how many flops are required to perform each iteration of this bisection method from exercise 5? Let you look at the code. How many flops are we doing here? Don't worry about the pre-work stuff. Let's just worry about each iteration of this for loop. So in the first line, we're calling the function at this midpoint. I see one flop to multiply x times x, and then another flop to subtract. So that's 2 flops. Then, the way we've written it, we have to multiply. So that's a third. And then we've got to calculate a midpoint. So let's say 5. Let's say 5. And yeah, I guess it would be 6 if we don't save y times sine. You know, I could be really fancy and make a variable called y times sine equals y times sine, but this is really overkill. You know, like sometimes it's okay to just be basic and give it another flop or whatever, especially in this class where we are not writing production code. We are just, you know, trying to learn. And so let's say this is 5 flops or 6 flops, but we'll just say it's 5. We'll say it's 5 flops per iteration. And then, what's the number of flops required to perform the calculation from exercise 5? Well, now we need to know how many flops, or sorry, how many iterations required. And in exercise 5, we were saying that we want within plus or minus 0.001 for my error, for my absolute error this time. Well, now I need the iteration count, 1, 2, 3, 4, and so on, and then the maximum error. After the first iteration, the amount of error I could still have left over is going to be 0.25. After the second iteration, it's going to be 0.125. After the third, 0.0625, and so on. So really, the relationship between error and iteration is going to be like 1/2 times 1/2 raised to the power I think. Because it's another half every time I do an iteration. And I want this to be less than 0.001. And we're trying to solve for this I, right? So multiply both sides by 2. And then, if I've got 1/2 raised to the I power is less than 0.002, and I want to solve for I need to take the logarithm base 1/2 of both sides. And the logarithm base 1/2, if you remember your logarithm rules, is going to be the natural log of 0.002 divided by the natural log of half. And I need my number of iterations to be greater than that number. I know this sounds crazy, but natural log of half is actually a negative number. And so whenever I divide both sides by a negative number, I've got to switch the, what do you call it? The direction of the inequality. I got to switch to the inequality. Okay, so I'm looking for a number of iterations that's as small as possible, but still greater than natural log of 0.002 divided by natural log of half. So let's take natural log of 0.002 divided by natural log of half. 8.965. So after 9 iterations, I should get to my desired level of accuracy. In our Python code that we wrote, we went ahead and did like 20 iterations, but it turns out I only needed 9 iterations to get there. And 1.415 is apparently close enough, or at least within that amount of tolerance we specified. Okay. So with 5 flops per iteration and 9 iterations required, that's 45 flops on the inside of that loop. And then if you want to complete this calculation, let's add up all the flops we have to do outside of the loop. And then to get the sign, we've got to do 1, 2, 3, 4, 5, 5 more flops. And so like 50 altogether. That would be 50 total. So as we evaluate numerical methods throughout the semester, there's going to be 2 things that we try to cut down on. We're going to try to cut down on the number of flops that are required to do each iteration. And there are certain methods that nobody would ever use because it just requires so many flops per iteration. And then we're also going to we're going to try to reduce the number of iterations that are required. Okay? And so in terms of the number of iterations required, bisection methods is one of the worst. It's going to require more iterations than other methods that get there faster. So that might be a reason you don't want to use bisection, but there's pros and cons. Everything has pros and cons. For right now, let's take a pause and see, does everybody understand why I said the error is 1/2 times 1/2 to the I power? Do you see how I got that? I basically was just looking at the error for the first few iterations and just kind of trying to guess the pattern. Okay, and then does everybody agree with how I found the number of iterations required from the error tolerance we were setting for ourselves? Yes or no? Let's look at that a little bit more closely then. I see some confused looks. So specifically, let's zoom in over here. My error was 1/2 to begin with. Because when I begin and I say my lower bound is 1 and my upper bound is 2, and I say the midpoint must be 1.5, the farthest 1.5 could possibly be from the true answer is a maximum of 1/2, right? From the edges. And then on each iteration, I'm cutting that interval down by 1/2. And so that's why I'm multiplying by 1/2 raised to the I power. That's what's happening every iteration. And I know that this has to be less than a certain number that we set for ourselves. And then we solve this inequality. We solved it by first multiplying both sides by 2. And then right here, what I want you to think about maybe is this. We'll do it a different way this time. I'm going to take the natural log of both sides of this equation. So now the right side of the equation becomes the natural log of 0.002, and the left side of the equation is going to be the natural log of 1/2 raised to the I power. And one thing you might know from properties of logarithms is that I can take the little lowercase I exponent out of the logarithm. Anytime you've got an exponent inside the logarithm, like if I had logarithm of x to the 5th power, that's the same thing as 5 times natural log of x. So let's take that exponent outside of the logarithm, and now I've got I times natural log of 1/2 is less than natural log of 0.002. And now what I'm about to do is I'm about to divide both sides by natural log of 1/2. And when I divide both sides by natural log of half, natural log of 1/2 is going to be a negative number. In fact, natural log of 1 is 0. Any logarithm of 1 is always 0. So if you're taking a logarithm of a number between 0 and 1, it's a negative number. If you're taking a logarithm of a number greater than 1, it's always positive. Okay? Here, let me show you a picture that I want you to have burned into your memory. Okay? This is the natural log function. This is the number 1. Do you see it has a 0 at 1? Everything below 1 is negative. Everything greater than 1 is positive. And then here is a log of every other base, right? Starting with basically 0 and going up to 10. Sorry, I guess I should start with 1. It doesn't matter what base I choose for my logarithm, as long as the base of your logarithm is greater than 1, where logarithms really make sense, then every logarithm of 1 is 0, and it always goes from negative to positive. Okay, so don't forget that. I'm sure that's going to come up again later. And whenever I have an inequality and I divide both sides by a negative, or multiply both sides by a negative, then I have to swap the direction of the inequality. So I say my iterations have to be greater than this number in order to work. And then we found out that was 9, or 8.9. Okay? So we're good with this one? Cool. All right, if you want to use the bisection method to find a zero of a continuous function inside the interval from 2 to 5, how many iterations are required to achieve an accuracy of 10 to the negative 6th? So let's work on this one. If my interval is originally from 2 to 5, then my original error from just calculating the midpoint of that interval is what? You say 3? Why do you say 3?
Because 5 minus 2.
Okay. Before we even start using the bisection method, one of the things we got to do first is we're going to just take the midpoint of the interval. Let me show you my code here. Like, I don't even consider the bisection method to really have started yet, because if I know my bounds, that the answer has to lie between 1 and 2, my initial guess is that it's at 1.5. And I haven't even really started to use the kind of like logic, the Bolzano's theorem, the bisection method stuff, until I enter this for loop. So right here, if I say that the midpoint between 2 and 5 is the number 3.5, that's what I mean by iteration number 0, right? So if I just have the midpoint, what's the maximum error I can get?
Distance from the end to the middle.
Yeah. What's the distance from the end to the middle? 1.5. Yeah. Because that's the distance from end points to midpoint. It's basically b minus a divided by 2. Okay, then after one iteration, how much error do I have? What's my maximum amount of error I could possibly have in my answer?
0.75.
Yep, 0.75. After 2 iterations, the maximum error I could have is 0.75. Yep, that's it. And so maybe we can now look at this and tell what the formula is. The maximum amount of error I can possibly have is going to be 1.5 times 1/2 raised to the I power. And I need this to be less than 10 to the negative 6th. Okay? So, solve the inequality for I. We do the same thing we did before. We're going to divide both sides by 1.5. Then we're going to take the natural log of both sides. And then we're going to divide both sides by natural log of half. Or I could just put the whole thing over natural log of half. Sorry. I'm making this too complicated, aren't I? But you could also write, the natural log of 10 to the negative 6th power divided by 1.5. That's the same thing as natural log of 10 to the negative 6th minus natural log of 1.5. So you could just write it like this instead. But then whenever you go to write your answer here, you would have to write natural log of 10 raised to the power negative 6 divided by 1.5, close parentheses, then divided by the natural log of half. Okay. And that's something you can put in your calculator. Let's try that. We get natural log of 10 raised to the power negative 6 divided by 1.5, close parentheses, divided by natural log of 0.5, and it's 20.5. And we have to be greater than 20.5, so the next whole number we round up to is 21. We need 21 iterations of the bisection method to get down to that level of tolerance, 10 to the negative 6. Okay, does that make sense still? Everybody's good? Yeah. All right, suppose I want the result of my calculation to have insignificant figures of accuracy. What error tolerance should I specify in my program? So now when we're choosing the amount of tolerance, sometimes, like in the engineering world, I'm thinking about calculations I've done in the past where I know that on the display, the software is eventually going to tell the engineer the final answer. It's not going to give them 15 digits after the decimal, right? It's going to cut it off eventually. And so if I know the display is going to round my result to 4 significant figures, then what's the tolerance I need to specify? Okay. And this is what I think about. Suppose we want 4 significant figures. And I hope you remember what significant figures are. Significant figures could look like 0.1234, like 4 digits after the decimal. Or it could look like something like this, 0.0001234. Those are both examples of 4 significant figures. Zeros in the middle count as significant figures, but zeros before leading zeros or trailing zeros don't count. The number 1234000, like 234,000, that also has 4 significant figures, right? These are all examples of 4 significant figures. So really the question is, how much error can I tolerate? And we're going to talk about this in terms of relative error. And relative error is the difference between my approximation and the real value divided by the real value. So ideally, my relative error is 0, right? When I close up that gap between my approximation and the true value. But it's not. So let me write it like this. The relative error is going to be this x hat divided by x minus 1. That's just another way of rewriting this. And of course, we're talking about absolute values here. So I don't know if that's actually valid. Let me think about this for a minute. Because the answer I think I'm trying to get at is this. Let me tell you what I'm thinking in my head right now. What I'm thinking to myself is, if I can get the tolerance for relative error to be 0.5 times 10 to the negative 4 minus 1, and my relative error can stay inside that tolerance, or less than that tolerance, then I should have 4 significant figures of accuracy. And so whenever I say minus 4 minus 1, that's really 10 to the negative 5 power. But I just put the 4 there so you can see it's really however many significant figures you want, that's where the 4 goes. I guess the reason why I'm thinking about this specifically is because if I had a true value of number 1, right? Then whenever I think about my relative error is going to be, according to this formula, my approximation minus 1 divided by 1. And dividing by 1 doesn't change anything. So it's just x hat minus 1. That's my relative error. And so if I guarantee that this is below a particular tolerance, then it should give me a certain number of significant figures, starting with the ones place. And how do I show that, though? I guess because if I had the worst possible approximation that still falls within this tolerance, it would be 1 plus 0.5 times 10 to the power negative 4 minus 1 or whatever. So it would be like 1 point. How many zeros? 5 zeros? 1, 2, 3, 4, 5, followed by the number 5. And then it would round up to being that. But then I still have, I've got one more sig fig than I need, actually. I think this is what I was thinking of. You can either write it like one way or the other, but I did both, and that's not good. Both of these would be right. Okay. So then, if I write it like that, I get 1 less 0 here, and so that should just be a 5. That should be a 1. And then I count 1, 2, 3, 4. Cool. All right. Thank you for your patience with this problem. Sometimes I have to think through it. Let me explain what I was talking about. My relative error has this formula. Let's pretend for a moment that the true value is just the number 1, because that makes calculations really easy. So we set this x equal to the number 1. if I divide by 1, it doesn't change anything. So I can say, if my true value is 1, my relative error is x hat minus 1 absolute value. Let's say this x hat is the worst possible approximation that I could have that would still fit under the tolerance. In other words, I'm going to have 1 plus the maximum error allowed by this tolerance, the tolerance itself, 0.5 times 10 to the negative 4. That would be 1.00005. And even if I tell my computer to round this up to the next thing or whatever, it's only going to contribute 1.0001. And if I'm looking for 4 significant figures, then the 4 significant figures here are 1, 2, 3, 4, and I can safely report 4 significant figures, and I can be happy that the calculation error left in my approximation isn't going to affect what I actually report. So, sorry for the long derivation here. But this is what I'm trying to say. If I need to report n significant figures, then we set the tolerance for relative error equal to 0.5 times 10 to the power negative n. And that's how you can calculate your tolerance. So if I want 6 significant figures, it's 0.5 times 10 to the negative 6. Okay, questions? No. Suppose we want to calculate the derivative of sine of x at the point x equals 1 using the definition of the derivative. Does a smaller step size always give a better approximation? I asked you this earlier in this semester, and let me try to find where I did that so we don't have to redo it. But the answer was no. Smaller and smaller step sizes do improve our approximation here, but only to a point, right? Taking a smaller and smaller step size worked great up until this point, and then the round-off error started started being the dominating factor in the error in the answer, and then it got worse and worse and worse. So there was actually an ideal step size somewhere here in the middle that worked nicely, where we still got a really, really small step size, but not so small that round-off errors mattered. And so the answer was no. And so one way I can set error tolerance in my code is I can set it according to how many significant figures of accuracy I need. I can calculate how many significant figures do I want, and I'll just make my code go to that point. Another thing that I might have, another situation, is what if I want the result of my calculation to have the best accuracy possible while still trying to avoid that round-off error regime, still trying to avoid the point where it gets worse because of round-off error. What error tolerance should I specify in my program? And the answer to this question, like what error tolerance should I specify, is something like this. Your tolerance for relative error should be going back to the data type we're using, the machine epsilon, times some kind of buffer, right? Some kind of safety net. Because obviously, from this picture, going to machine epsilon was a bad idea. That was creating more error than we had if we had chosen a larger step size. And so we need to back this up a little bit. And in order to find out how much we need to back this up, it could be a good idea just to experiment for a minute. Like, what if I did, this is powers of 10, right? So how many powers of 10 would I need to back off of machine epsilon? 1, 2, 3, 4, 5, 6, 7. 7 or 8 even, just say 8 to be safe. This might have to be your machine epsilon times 10 to the power 8 or so to get a safe tolerance. When we talked about how to find machine epsilon in our first lecture, it was like some power of 2. It was like 2 raised to the power negative the number of bits you allocate for your mantissa. It might have been -1 at the end of that. But you're going to leave some buffer. You're going to multiply by a safety factor, basically, to keep you away from round-off errors and to make sure you're in that safe zone. This probably won't get you close to how many significant figures you want, but if you were doing some kind of high-level scientific computing, I guess what you would do is you would decide, I need so many sig figs of accuracy. Maybe you need 10 sig figs of accuracy, and you calculate your tolerance. And then you would look at your data type you want to use. Maybe you want to use double precision floating point data type. Find out the machine epsilon, multiply by some 10 to the 8th safety factor, and then see what that tolerance is. If this tolerance is telling you a larger number than the tolerance you want from having 10 significant figures, then you've got a problem. Then you've got a choice. You can either compromise and go for fewer significant figures, or you would have to choose a bigger data type, like a quadruple precision floating point data type. But that's the idea, is you want to choose your tolerance based on the number of sig figs you're going to eventually show to the final consumer, the final user of the data. But you also need to double check and make sure you're not getting too close to machine epsilon. So we're almost done here. If I ask you in the future, what is one major strength of the bisection method? This might not seem super obvious, but the biggest strength of the bisection method is it always converges for continuous functions. If you're dealing with a continuous function and you know the bracketed interval to start with, where one side is positive and the other side is negative, then it always converges to an answer. Of course, again, that's if f is continuous. And that's if you have a good starting interval. We're going to talk about this a lot more in the coming lectures, but what are two considerable drawbacks? Well, number one, it's slow compared to other iterative methods we're going to talk about. Bisection method is going to converge slower. It's going to take more iterations than other methods will. And number two, another drawback here is we have to know A and B. In other words, we have to come up with a starting interval. And that's not always easy. Sometimes you have a function that somebody hands you, and you don't know where a valid starting interval would be. This could be hard for two reasons. I'll just say this really briefly, because what we started at 1:45. Oh shoot, I've gone 2 minutes over, haven't I? So it could be hard for two reasons. Number one, the function might cross the x-axis at a huge number, like 10 trillion, and you just don't know how far you need to put the upper bound. The other thing that could happen is maybe you've got a situation where your function crosses the x-axis and crosses back over in a really tiny spot. And so you keep sampling points of your function, but every time you sample your function, you only get positive values, and it's really hard to figure out how to find a negative value to even start with. So that could be difficult. Sorry. All right. Thank you, guys.